Good morning. Are you able to hear me now?
Yes, sir.
Okay. I wanted to try something different, using my physical whiteboard to explain things, but that experiment did not go all that well. Postpone it to class. So, bunch of announcements before we begin. So tomorrow we will not have a class, but what we will do instead is I'll post a couple of quizzes that you can take. They will follow the usual rules, 12 minutes plus 3 minutes, and at an interval of maybe about the first one will start at some point and the second one will start about 25 minutes later. So, I'll set it up that way. And we will also have a session just to take care of any lingering questions and stuff that you may have about phase diagrams. So we can do that this evening. I guess you all have some lab, at least a part of your class has a lab this afternoon. So maybe we can do this at 5:30.
Yeah, I guess 5:30 is fine with most of us.
Okay, so as always, this is not compulsory. This is meant essentially for people who may have some things or the other that they want to ask me. And I think such a session is always useful before the quiz. So we'll do one today at 5:30. I will send you an invite, and so we'll all get.
And this quiz will just be on phase diagram, right?
Just on phase diagrams. Yeah, whatever we are doing now, which is phase transformations, is not covered, though they are related. So, but we will take up phase transformations in a separate set of quizzes.
Also, sir, you said that you'll be sending some guidelines for the term paper because we don't have any experience in writing papers or anything as such. Like we have never written them before.
Right. Thanks for reminding me. I was going to make a comment about that. But broadly, the topics are in, I mean, you can classify them into all kinds of categories. In some cases, they fall into 2 or 3 more or more categories as well. So by and large, they are about a specific material, or they are about a class of a specific class of materials. And in some cases, we are talking about specific properties, and you can have multiple materials which sort of exemplify those properties. For example, if you're talking about hard material, what is the thing that comes to your mind? What is the hardest known?
Diamond.
So things of that nature as well. In fact, the next term paper is something that I hope you'll find interesting. So there are again, what are the examples that you know of where materials performance will have to keep improving, like day by day, month by month, and so on. There are some everyday examples. Just name some.
Materials that I used to make lenses.
Okay, lenses. Yeah, cameras basically.
Both. I mean, I was talking in context of spectacles, but yeah. The same
okay,
idea.
sure, absolutely, yeah.
Scratch
And
resistance.
also our mobile phones. They keep improving in performance, but mobile phones, I mean, there is it's a combination of materials as well as device technologies, right? But there are specific materials that help in help the designers in designing better models and faster and more miniaturized models and so on and so forth. So, for example, cameras have been getting better and better, cameras in mobile phones. And our mobile phone display has been getting better and better. And so if you look at the display technology, I mean, you'll find a whole bunch of materials. They will mention them in the form of technologies, but I mean, some of the materials that may come up there would be LED type displays. Earlier days, the first generation of mobile phones had the LCD displays. And the LED, then even within LED, there are multiple variants. And Samsung seems to specialize in OLEDs, organic LEDs, and so on and so forth. But how about automobiles? There are everyday automobiles like Hyundai and Swift, I mean, Suzuki and stuff like that. And there are high performance automobiles which participate in races. Same with bicycles, motorcycles, and so on and so forth. There are high performance versions of everyday stuff. And the other kinds of domains where high performance is required, both on the device side and on the material side, they would all involve strategic technologies, space, defense, and atomic energy, and so on and so forth. So, I mean, in all these cases, whenever you talk about a specific material, I mean, you look at what it is meant for, and in some cases, a material is meant to achieve multiple objectives. And so therefore, you tailor the material, a single material, but within that you try to incorporate as many features as possible. For example, high temperature and high strength is something that the super alloys are meant for, and so on and so forth. So that is going to be the main focus, where you will get to choose your own topic. You just choose an interesting topic. In sports, for example, you have, I mean, tennis rackets, cricket bats, as well as cricket balls. Then in football, I mean, the ball technology has been changing as well over the years. And something that I learned recently in swimming, a particular kind of swimsuit, full body suit that many people wore in 2008 Olympics. A whole bunch of people beat the world record in that event, apparently. And that thing has been banned now. So the material itself is not banned, but the full body swimsuit is banned. And there are shoes, high performance shoes that all these sports companies want you to buy, even though you may not be doing any high performance activity. In running, I heard about something called Vaporfly. So just take a look at these things and write about some of the interesting materials that go in there. So in all these cases, I mean, just focus on things that you have learned in this course. And we hit on specifically some 4 or 5 topics in this course, and that is what is sort of at some level a common core for studying all of materials. The first one, of course, is crystal structure. And if you go to the glasses, it is a lack of crystal structure which produces some interesting properties there, and therefore, okay, crystal structure or lack thereof is one. Phase diagrams. So anytime you, and of course, you want to talk about whether the material is an alloy or a pure substance. And even for a pure substance, a compound, for example, you have to ask questions like whether it is a stoichiometric compound or a non-stoichiometric compound. And if it is a non-stoichiometric compound, then you obviously have to ask questions like, how is it achieved, and what does that non-stoichiometry get you in terms of performance boost for the properties of interest for that material. So just learn something about the material and say something interesting about the material in terms of these topics. And of course, phase transformations is another thing that we are going through right now. So either during processing or primarily during processing, I mean, some phase transformation may be involved. And so you talk about the fact that a phase transformation is involved, and that somehow helps improving the property. And so you can pick any domain. You can pick things in electronic domain or structural domains. By structural, we basically mean mostly mechanical properties. If you stick to mechanical properties, it would sort of align with the bulk of our course, because that is what we are talking about most of the time. But if you wish to choose some electrical or electronic properties, that would be okay with me. Yeah, somebody has a question. So Anubhav Goswami.
Yes, sir. The things that you were saying right now, are they relevant to this term paper or the next term paper?
Both. It doesn't matter.
Okay.
So in all these cases, I just want you to hit upon these specific things. And of course, there are also interesting things about the way they were developed. In some cases, they were developed either because there was a felt need and there is a targeted development. For example, as you probably know, during the Second World War, the atomic energy program in the US, it was put together under something called the Manhattan Project. And so it is all designed. So there was a whole bunch of people who studied the nuclear behavior of all these interesting nuclear materials. And there is this other class of people who decided to, who were given the task of developing the surrounding infrastructure in terms of materials that will contain the things and so on. And so everything, there was some theory to guide this process, but a lot of it was still trial and error. And what kind of materials would withstand radiation is something that was not known at that time. So things needed to be done essentially on a war footing in a mission mode. And so we have such mission mode organizations here. ISRO takes care of space-related things. And they probably have some plans for things that will happen over the next 6, 8 years, or maybe even 15 years. And they will start making plans for the corresponding developments in all the related fields. And materials would be a major part of that exercise. Same with atomic energy, same with defense. Defense, probably has plans for 2035, what kind of defense preparedness that our country needs to have, and what are the things that we need to put in place, especially if you are interested in developing our own technologies, and so on. So, and there is also this other interesting angle which you may or may not appreciate, which is that there are some materials which are available, whose raw materials are available in specific countries, and they need not be our friendly countries. For example, rare earths. The primary, major sources of rare earth materials, they happen to be in China, and we know the kind of problems that most countries have with China, and because of that, almost every major country would have major programs running for developing materials for things that exist now, which use rare earths, and try to get them to work without, or at least decrease the dependence on rare earths in those materials. Same with lithium. Lithium also has a similar issue, though it is not as critical as in the case of rare earths. So you want to sort of move away from lithium, and lithium, of course, is the most critical material in batteries. So you want to come up with battery technologies which move away from lithium-based batteries. Magnesium-based batteries are being talked about, but early stages, I suppose. And so we have somebody in our department and also in MRC who are working on all kinds of interesting battery technologies. Sai Gautam Gopalakrishnan in our department is working on certain theoretical and computational aspects of these novel battery materials. And battery related work happens in several other places also, but in MRC, Prabir Barpanda has a nice experimental group which is exploring various battery technologies. I wouldn't know the details, So that kind of stuff. Again, moving away from lithium, and wherever it is possible, just to replace lithium altogether. Many ground-based things where people are not carrying things with them, like in automobiles or mobile phones. I mean, you can develop there exist battery technologies which completely get rid of lithium, but they also have other materials which may or may not be easily available in India or in the country that is interested in developing these technologies. So there is a class of batteries called flow batteries. These are liquid-based batteries, and obviously they are useful only for situations where you want to store a lot of energy. But ground-based, these are not mobile things, so you use that for storing energy, and whenever there is demand, you release the energy into the grid and so on. So large-scale batteries of that kind are also being talked about. But the fashionable stuff, of course, is the lithium-based batteries and their replacement. So strategic things may also drive the need for new materials and newer high-performance materials. Okay, I see a couple more raised hands. Okay, somebody called Karthik. Just 1 second.
Sir, last week you told us that the quiz is going to happen on Thursday. So,
okay, since I am tied up tomorrow, that is why I'm trying to do this tomorrow. But if you want it on Thursday, we can still do it on Thursday. In which case, I will need a makeup. I will need a makeup class for tomorrow's class. That's all. So that's okay.
Sure. We just want it on Thursday.
Okay,
and secondly, what is the deadline for the term paper, the first one?
5th. I will put down all these thoughts in some coherent fashion and send it across to you. January 5th is the deadline for the first one, and about maybe a couple of weeks later is the deadline for the second one. Second one is that takes us pretty close to the final exam. So if you want, I can even give 4 days after your last final exam is done, and we can use that as a deadline as well. That's not a problem for me.
Sure. Yeah. Sure.
Okay. So yeah, one more.
So
yeah,
the files you put up, you also said that if we want to work on a topic that's of more interest to us and not on the list, then we can send a mail asking for a change. So
please do. Have you done it already?
Yes. No. So that's what I'm asking. When do you expect us to do it? When is the?
Hey, at least 6 people have already written, and I have written back to them. So it doesn't sit in that mailbox. Even if I forget it, my TAs remind me. So that has happened once, and so it gets done. January 5th is the deadline. So what are you waiting for?
Yeah. Okay, I'll do it today.
Right.
So I mailed you last night about the change in topic, but I haven't received a response.
I haven't looked at last evening. I mean, since yesterday, I haven't looked at the mail, at least for this kind of request. So I'll take care of it today.
Sure. Thank you.
Yeah. Anything else?
Sir?
Yeah.
How lengthy do you expect the write-up to be?
About 2 pages, including references. Referencing is very, very important. You should learn how to reference your sources. Obviously, the stuff that you're going to write is not coming out of your imagination. So it is coming out of various sources that you have used. It could be a YouTube video, it could be a Wikipedia article, or it could be a scholarly article. So I believe in these times, most of your sources would be online. So, but wherever, just give the online source. And obviously you are going to, if you sort of examine some 3 or 4 different sources for one little thing that you want some clarity on, maybe you will need only one of them. And so it's very important that you cite your sources. Not citing your sources is seen as some sort of a crime within academic circles. So try to be original, but the other thing is very important as well. Whenever you put something down in writing, it's a good idea to write about what you know, what you have learned rather clearly. And if certain things are not very clear, you are welcome to say that I'm not particularly clear how this works, but this is something that I learned. That's still okay. But wherever you are really sure about your sources, and that is also another important thing that you will have to develop. You need to know who are the reliable sources and who are not. And Wikipedia in many cases is a reasonably reliable source, but it may not always be so. Academic papers tend to be reliable, but I mean, if you've been following some recent debates, some of the academic papers in certain fields are also not all that reliable. So write something, find something interesting about your topic and put together a little story and try to connect with things that we have learned in class. That is what
Is the 2-page deadline a very hard deadline?
Okay. What do you want? I mean, put forward your request and we'll negotiate.
But 2 pages is too less. Like we'll start and it'll end.
Okay, I mean, hey, a 2-page is something that I expect from you. You want to write an 8-page essay or a 40-page bachelor's thesis? I mean, I have no problems. But even in a 40-page bachelor's thesis, you'll still have to provide a 2-page abstract, which hits all the main points. So, yeah, I mean, 2-page is a guideline. You want to write longer pieces, that's okay. I have no problem.
So
don't make it short. Don't give me 1 paragraph and some 4 references.
Hello.
Yeah.
Sir, so when do we expect the second term paper and how is it going to be? So
okay, just now we discussed it. I presume you missed it, but I'll send a note, and that's going to be things that you are going to pick on your own. And so from a certain class of domains. So these are basically high performance materials.
Okay, sir, in that case, can we get the deadline for this one extended for at least a couple of days? So because we had midterms on 26th, we kind of got all work in that week. So
all right, I can. Okay, Jan 5th, I think is a Wednesday or something, so I can push it to that Sunday.
Yeah, thank you, sir.
All right, that's not a problem. So let's go through this exercise, but let's also not make it horribly complicated and painful. So that is, let's work towards that. Yeah, one more question. Okay, that went away. I still see some hands raised.
So just to confirm, the quiz will be on Thursday, right?
Yeah, that's correct. I'll post a note. In fact, you can post a note right away in this thread. So that people who are not here would also get yeah, just post a note saying that it is confirmed that the quiz is going to be on Thursday, but we will still have a session this evening at 5:30. And if there is a felt need for more such sessions through tomorrow and Wednesday, we can do that as well. In fact, I mean, why don't one of you, somebody who wants to come forward, why don't you just send a meeting note to this this whatever this is called, general channel for this course. Send a note.
Sir,
yeah, go on.
So is it supposed to be typed or handwritten, or can we do either?
Please type it. Please type it.
Okay, sir.
Okay, so the evaluation is primarily going to be on the essay part, certain aspects of essay, the clarity with which you are able to describe things, definitions and this and that. You are referencing your source material and the narrative that you put together about your topic. What is sort of interesting about that topic? And if you don't dig too much into this, because it's a rabbit hole that can take you. I mean, online, you know how it is. It can keep taking you to all kinds of places, and you will simply end up spending a lot of time. But if you are able to find something interesting in history of the development of that field, whatever you're researching, say something about that also. And I mean, maybe something scandalous happened, maybe some major accident happened, and or whatever. And if you are able to talk about those things in your essay, okay, think of the essay as some sort of a narrative as in storytelling. So put together a nice little story. Obviously, it is non-fiction, and so just put together something interesting about this stuff. Okay, hey, we have already spent a lot of time on this. So shall we quickly? So Wednesday night at 10 is when we are going to do Shashank's lecture. So let's. It should be a fun lecture. Shashank is a very interesting guy. He joined the UG program in 2012, and I mean, I got to know him when he took my course about 1.5 years later. Those days and these days, even now, I teach thermo in the 4th semester. That's when I met him. And by then, I mean, the guy had already decided that he wanted to work on additive manufacturing. At that time, it went by the name 3D printing, primarily. Additive manufacturing was still being talked about. And so much so that he was so interested in it that he went ahead and spent some money on some Kickstarter funded startup. And I mean, you know how these things work, right? Crowdfunding. So they collect money from people on the saying that they will develop a product and they will make it, and whoever funds this at a sufficient level will get the product. One of the initial things that they make actually eventually end up making. So he waited for a year and then got it. So that is the stuff that he is referencing in his abstract as well. I'll send you the abstract today. So he actually had a 3D printer, possibly the first 3D printer in IISc. And I'm talking about all of IISc. I mean, not just among students. And since then, I mean, he finished in 2016, went and got a master's. And since then, he has been working in, he has worked in 3 different companies, I think, but 2 of them are where he's, okay, one he spent a long time at, and that is a startup from MIT, additive manufacturing startup. He spent close to 3 years there, I think. No, it can't be 3 years. 2017, yeah, about 1.5 years or so. And then he moved to another company as an interim arrangement. And now he is with a 3rd company, which again is into additive manufacturing. I don't know how many of you saw this, checked out this website for gantry.com. I mean, they have some serious eye candies there. Really lovely looking lampshades and stuff. Very expensive as well. Just one lamp arrangement costs about $200. Anyway, so they're all LED based lighting, home lighting, and that's where he's working. So he wants to talk about his journey. So I made a request to him to talk to the students. By the way, I mean, would you want to talk to more such seniors, people who have graduated as well as people who are still here?
Yes, sir.
In which case, I can organize some such stuff. So, because I'm still in touch, especially with the first 2 batches. I was the materials coordinator at that time. So I'm still in touch with some of them, and I can ask them to come forward and talk to you. And they have all gone into all kinds of interesting careers. This guy went into industry, somebody, by the way, the first PhD student from materials, that person just finished this August from the 2015 batch, very first batch. Her name is Neha Kandekar. So she's the first PhD from our materials stream. Yeah, I'm in touch with others. There is a guy who went into management, and so it's only a matter of tracking him down. And in between, you probably listened to Anubhav Jain, who went into finance, investment banking and stuff.
Abhinav Jain, right?
Yeah.
Yes, sir. Yes,
Yeah.
sir.
So he also belongs to the materials batch, the first batch in the materials stream. So I'll try to get other people to come forward, and we'll do it maybe over the weekend sometime. Since they're all over the place, I mean, we'll have to worry about time zones as well, but we'll do that. At least one or two more I will organize with your seniors. And there are, of course, seniors who are already still with us, people in the 3rd year, 4th year, 5th year types. And maybe I can ask some 2 or 3 of them to come forward, and then we can have one joint session just so that you can talk to them. Okay, let's just quickly switch over to the topics that we want to cover today. You've all gone through this stuff. You have any specific questions? If not, I mean, I'll just have to go through it in some sequence, I suppose. So, okay, I forgot to share the screen. There it is. Okay, we want to talk about precipitation as one of the it's one of the simplest phase transformations that you can think of, and the water sugar phase diagram is something that we started with quite some time ago, so at something like 80 degrees Celsius, water can hold this much of sugar. That is, we are talking about what? This is sucrose weight percent. 80 grams of sucrose, or 800 grams of sucrose if you want to think in terms of 1 kilogram, and 200 grams of water, well, that would still be a solution. And if you cool it down to a lower temperature, such as 40 degrees or 20 degrees, obviously a whole bunch of sucrose will have to come out, because what you have is you are in the two-phase region of the phase diagram, and we call this precipitation. And I do talk about this later as well. The main main difference between precipitation in this and precipitation in solid materials is that the sucrose that comes out, well, the usual problems of nucleation and growth, all that will happen, of course. But once some crystal is formed, then it will start sinking to the bottom because of the density differences. Liquid allows that, whereas in the solid state, such a thing does not happen. So wherever they are nucleated, precipitates are nucleated, they just stay put, and you can see them in the microstructure. I have another presentation where I want to show you the diversity of microstructures that are possible here, and anyway, we'll move on. The nickel-rich end of the phase diagram is relevant for, the nickel-based superalloys. This is the prototype binary alloy for the nickel-based superalloys. There are corresponding superalloys that are available on based on iron and cobalt as well. And in cobalt, I mean, we have a couple of people. It's a really new field, very young field, and we have a couple of groups that are leading groups in their work on cobalt-based superalloys. Professor Kamanyu Chattopadhyay and Professor Surendra Makineni, who joined us just in about a year ago, so January 1st of this year. They have done some really fabulous work, and they continue to, because these are things that are still under development. Anyway, they all share similar microstructural features, which unfortunately I will have to defer to the other presentation, which I have, and I'll post it also on as additional course material. Anyway, so if you take an alloy with about 80% nickel, this is atomic percent, by the way, there is weight percent which is up here. And you can see that this scale is obviously different from the scale here because of difference in atomic weight. Anyway, so 80 atomic percent nickel at something like 1400 degrees Celsius is still in the form of a nickel-rich solid solution. So that is 80% nickel and 20% aluminum in the form of FCC solid solution, randomly mixed up. Nickel and aluminum atoms are intimately mixed up at the atomic level. So if you scoop a little bit of it out and measure the composition locally, you would find the composition to be roughly in the ratio of 80 to 20. But on quenching it to some lower temperature, then it enters this two-phase field, and the two phases are this nickel-rich solid solution and this phase here, which is AlNi3, Ni3Al. And this is called, the FCC solid solution is called gamma, and this one is called gamma prime. Again, let's not worry too much about the terminology here, but it is basically a two-phase. You enter the two-phase field by going up to some high temperature and quenching it. Even though we will be talking about it in the context of situations where temperature change causes the material to go from a single phase region of the phase diagram to a two-phase region, thereby going into a situation where it has to get the second phase out. Precipitation is pretty much the name of the game in all the groups where they study nanoparticles. So you develop some interesting solution involving various components and get them all into solution. And there you change the condition not in terms of temperature, though that may also be involved, but usually you change some other condition, which is in terms of the composition of the solution, primarily the acidity of the solution. But you could, I mean, chemists are very, very clever in coming up with all kinds of interesting ways of making these particles at low temperatures using soft chemistry routes. And there are multiple things that are involved. But what is common among all of them is that instead of a temperature quench from high temperature to low temperature, where you go from single phase to two phase, there you do a composition quench. In the case of pH, for example, suddenly you add a little bit of acid to decrease its pH, and suddenly the system finds itself in a zone where at equilibrium, it wants to have two phases. And so you can produce nanoparticles this way. And of course, if you do it in a controlled fashion, you can produce some really fabulous nanoparticles with all kinds of interesting properties. So Professor Ravi Shankar's group in MRC, Professor Chandan Srivastava's group here. By the way, I mean, much of ceramic materials are also made using such soft chemistry routes. And they all depend on producing particles using methods such as this. But they would all be classified primarily as precipitation because you are changing the condition where the system goes from some place where it is stable as a single phase to some other place where it is stable in the form of two phases. And that means the second phase has to come out. And so the transformation itself is represented in this fashion. This SSS stands for basically supersaturated solid solution. So the solid solution that is quenched into the two-phase region initially is supersaturated, and you wait for a while and slowly this gamma prime comes out in the form of precipitate phases. The usual issues that we have discussed in the case of solidification, they occur here as well. So there is a nucleation barrier. And so when we talked about nucleation, this came up as an important equation. The change in free energy, the driving force for precipitation, the change in free energy associated with formation of a small cluster of the precipitate phase, again has this form. It has a volume term and there is an area term. And this delta GV, there it was easy to see from the free energy versus temperature curves. But here we use the free energy versus composition curves. It's a little bit more complicated, but it exists. It has a very clear definition. So the procedure for computing this is a bit more complicated. But here are the things that you need to know. So just like delta GB is 0 there at the melting temperature, here it is 0 for an alloy at the solvus temperature. That is in the case of 80% alloy at this temperature, the delta G for delta G sub V, the volume free energy change associated with precipitation is 0 at the solvus temperature itself. And of course, it is 0 for any finite undercooling. Undercooling itself can be described in this fashion, T sub S minus T, and where T is the relevant temperature to which it has been quenched. Analogously, we can also use supersaturation as an indicator for, the tendency to precipitate. And that would be defined in this fashion. This is the alloy composition. This is the C gamma. Again, at the lower temperature, the composition of gamma given by the solvus is this C gamma. And of course, when delta GV obviously is negative, when the alloy is undercooled or supersaturated, larger the undercooling, larger is the magnitude of delta GV. All those things carry over quite nicely from our discussion of solidification. All right, so we have already talked about this density differences causing a certain interesting possibilities. In the solid, of course, the precipitate just stays put. Wherever it is nucleated, it just stays there. It only grows bigger or smaller depending on the conditions, but it just stays there. And the other main thing is this: diffusion in the solid state is 4 orders of magnitude slower than in liquid. Well, this 4 orders of magnitude is valid near the melting temperature, and it becomes even slower, right, by even many more orders of magnitude as the temperature drops. And for example, diffusion of in nickel alloys is practically zero at temperatures below the below 50% of the melting temperature. That has something to do with diffusion, which we haven't discussed in detail. We'll spend some time on that topic a little later. Maybe I'll put together a half-an-hour lecture. But right now, I mean, this is generally true for all these substitutional alloys, where the two elements sort of substitute for each other in the lattice. For interstitial alloys, such as carbon and iron, this limiting temperature goes down maybe to about 20–25% of the melting temperature. All these are guidelines, and there is a very strong reason to believe these guidelines. And there is a strong scientific basis as well. Different materials will give you a different prefactor here, but by and large, as you come down to lower and lower temperatures, diffusion is practically zero at extremely low temperatures. So at low temperatures, extremely low temperatures, if you quench this nickel alloy from 1400 or whatever to room temperature and hold it there, you would not see any precipitation whatsoever. Precipitation requires aluminum atoms to come together to form this Ni3Al precipitates. And that requires diffusion. Since diffusion is practically zero, the entire thing can be completely wiped out. It will remain as a solid solution at room temperature for, I mean, years and years to come. So evidently, this implies that at extremely high temperatures near the solvus, the driving force is zero, because of which the transformation does not really happen for a long periods of time. And of course, at extremely low temperatures, again, it does not happen because of diffusion. And so one typically is looking for some window which is between the solvus temperature and this limiting temperature below which this becomes basically diffusion becomes zero. All right, the next topic is eutector transformation. This is the iron-carbon phase diagram. Carbon, as I just now said, is an interstitial solid solution. Iron itself goes through. This is the iron, pure iron. The entire phase diagram is only restricted to this 6.7, which stands for Fe3C. If you do, this is weight percent. So if you do the calculation for the amount of carbon in terms of weight percent in Fe3C, it would be that. So beyond that, I mean, one typically does not go beyond this. It's mostly carbon and iron. So I don't think there is anything interesting there in terms of the phase diagram or its uses. Even within this small region, there are interesting things. Pure iron goes from BCC form to FCC form at high temperatures. And of course, it goes back to BCC form before it melts. And so in the FCC form, it has a lot more solubility for carbon. You can go up to 2–8% carbon here. Whereas in the BCC form, it has extremely limited solubility for carbon. As you can see here, it is 0.02 weight percent. This is percent, not fraction. So extremely tiny amounts of carbon can only be dissolved in the BCC form. And together, they form this eutectoid, which is the solid state, fully solid state equivalent of eutectic, where gamma transforms to alpha plus Fe3C. So that is the low temperature two-phase region. And if you take an alloy, which is the eutectoid alloy itself, into this temperature range around 1000 degrees Celsius, then it is in the form of single FCC solid solution of carbon in iron, and you bring it down to a temperature below this. This gamma will decompose, will vanish from the scene, and it will produce Fe3 plus alpha. They all have names, and I think I've given the names here. I mentioned it somewhere here. Yeah, the BCC form, low temperature BCC form is called ferrite. The high temperature BCC form is simply called delta iron. And the intermediate FCC form of iron carbon stuff is a solid solution is called austenite. So it's a good idea for you to remember these things. And there are these other transformations. There is a eutectic here and there is a peritectic here, and we will not talk much about those things. But this is something that is of interest because pretty much all of steels, they have to go through this, or they have to do something to avoid this in some fashion. So eutectoid, which is why, I mean, the steels, the definition of steels is restricted to something which has less than 2% carbon typically. And of course, it can also have other alloying elements, but treat this as some sort of a prototype. All right, you take this alloy into the single gamma phase and you hold it, bring it down to some low temperature and hold it. It forms alpha ferrite and cementite. And just like the eutectics, so eutectic solidification produces lamellar microstructure, this also produces lamellar microstructure. Here is the microstructure, and you can use the lever rule to find out the thicknesses, relative thicknesses of these things. And you would find that it is typically, I mean, near equilibrium conditions, it should be 1 to 7.5 or so. All right, and just like in the case of eutectics, this lamellar microstructure provides an efficient way to make this transformation proceed. So alpha is this ferrite, which is the larger volume fraction phase. That 7.5 to 1 is what I mentioned. So if the cementite thickness is 1, this is about 7.5 or so. So this has very little carbon. We have already seen that, but Fe3C requires a lot of carbon. So this provides a very nice way in which carbon with its intermediate composition in austenite can be redistributed. Carbon can go straight to along the interface to Fe3C, allowing for it to migrate forward. And as this region becomes lean in carbon or richer in iron, this guy alpha can also move forward. So it provides a very nice way of redistributing the solvent and solute atoms. And it also allows for the cooperative growth of these things. Okay, off eutectoid, if you take an alloy such as this, the first thing that happens is precipitation of alpha, because this is some sort of a solvus in reverse. So single alpha, I mean gamma phase, you bring it down to here, it has to come out, alpha has to come out of that alloy. And typically it comes out at the grain boundaries for reasons which have something to do with the crystallography. We won't go into it, but it produces this really characteristic microstructure. Alpha basically decorates the prior austenite grain boundaries, and the interior, the remaining stuff, undergoes pearlite transformation, which in this picture is not fully resolved. The alternating lamellae are not fully resolved because you see the micron marker here, it is 200 microns or so, whereas those things would be extremely tiny on the scale. The interlamellar spacing there would become. All right, you can do the same thing with by going to the other side as well. In this case, the cementite has to come out, and the cementite again comes out at the grain boundaries due to primarily crystallographic reasons. And so you end up producing decoration of the prior austenite grain boundaries with cementite, and the interior again undergoes pearlite. Undergoes this eutectoid transformation, producing alternating lamellae. The alternating lamellae are called, that microstructure is called perlite. Anyway, so this is where we stop with this lecture. But in the next lecture, which is probably going to happen this Thursday, towards after the tests are done, I'll show you some interesting microstructures, the variety of microstructures that are possible in the solid state. And that is what makes material systems really interesting. Okay, we'll stop now. Sorry, I went about a couple of minutes over. Okay, I mean, since we are out of time, we will postpone any questions to Thursday. And unless, if you don't have a class, you can linger around. We can have a quick discussion. But if you do have a class, please proceed. Okay, right now I don't see any raised hands. So,
sir, I had a question.
Yeah,
in
go
the AI, sorry, in the aluminum nickel phase diagram. So could you, okay, before that, so like, I mean, I don't understand this quite well. So some phases are represented by Greek letters alpha, beta, but then some others are given a chemical formula. Like I didn't quite understand why. Like, I mean, I understand that.
Yeah, there is no rhyme or reason for any of this stuff. So it depends on how that particular small community deals with this stuff. Okay, so let's not worry too much about it. The same thing that we call gamma now in the nickel aluminum phase diagram, in some other nickel X phase diagram may very well be given a different name altogether. So don't worry about it. It just says something about the history of the development of that small subfield. The first set of guys who decided to work on nickel-based materials probably decided to give this guy a name such as gamma.
Sir, another question I had, I think I might have missed this when you were explaining. So certain phase diagrams are called eutectic, peritectic, and all that, right? So I didn't like understand this naming. So in Callister for eutectic, they were saying it has this typical character that it will melt it will melt very easily below both the melting temperatures.
Okay,
but
I mean,
I was not sure of why the names for this, like eutectic, peritectic, and so on.
I have no idea either. Okay, these names are stuck, so they are sort of hand-me-downs now. So we are stuck with those names. There probably is a good reason for these things, except that it is never really explained anywhere. If I find something, I'll tell you. I've been teaching phase diagrams in thermo for the longest of time, and this question does come up every once in a while, and I have not been able to find any good reason for why something called eutectic, as if, I mean, it's a good tactic as opposed to a bad tactic. I don't know.
And also, like you mentioned, we could calculate in one of the slides. You mentioned we could calculate from the lever rule, we could calculate the thickness of the grain. I didn't quite follow. So, like in lever rule, we'll get the composition of each of the pure phases. But how do you go from
fractions and the phase fractions?
Right. So how do you go from that to the thickness?
Okay,
right?
you compute the phase fraction of alpha, and you compute the phase fraction of Fe3C, and look at what the ratios should be. I've already given an indication there. If you look at the slide there,
I was thinking it will depend on the the shape of the.
It will depend. No, that is just fraction. That is how much material you expect, and that is in the form of weight fraction, right? So if you take 1 kilogram of steel, so much of it would be in the form of Fe3C, and so much of it would be in the form of alpha. So many grams. That is why I said, if you assume that the densities are nearly the same, then you would expect their relative thicknesses. You know the microstructure now. They are alternating lamellae. So you would find the alternating lamellae to have that kind of ratio of thicknesses.
Okay, so from here we'll get the relative thickness, and then by measuring any one of them, we can get both of them.
No, relative thickness is in the ratio. I'm only giving you the ratio, 1 to 7.5 or so, approximately.
Okay, fine. I think I assumed it to be the actual like thickness.
No. So the actual fractions you can compute. It is 1 by 8.6, for example, 8.5 for Fe3C, and the other one will be 7.5 divided by 8.5 for alpha. That's all. So that would be the phase fraction of alpha and Fe3C.
Okay.
That is lever rule. That's all. Nothing. I mean, nothing fancy there. Okay, use lever rule blindly and take the ratio, and you would find that the ratio will be about that. I mean, it's all approximate stuff, 1 to 7.5 or so. Okay, anything else?
No, sir.
Okay. Well, like as usual, I'll linger. I mean, if you have something else to go to, please, you can leave. And somebody will have to eventually stop the recording, I suppose. And since the recording is available, I mean, people can always take a look at it later if they need to. Okay, see you all on Thursday then.